Yeah, right. For everyone, for today's lecture, so what I am going to do is remember that last week we derived the Lagrange equations, and then we started looking at few examples, right? And so it is my understanding that you should realize now that how easy it is to use the Lagrange equations for complex situations. When you have complex problems that you have to solve, it is always easier to use the Lagrange equations rather than Newtonian equations, right? And plan for the today's lecture is, in the first half I am trying to introduce you another method that we can use to derive Lagrange equations. Now this is based on something called variational principle, and sometimes the students who are doing applied maths or industrial maths may already know about this method because this is not limited only for classical mechanics. This principle which we called as the variational method is used even in quantum mechanics and also in some other branches in mathematics as well, right? Now this theory arises from a question that scientists had when we so I'm assuming that all of you can see my shared screen right now. So if anybody can't see that, please let me know, right? So today's lecture will be about variational principle. Now this theory actually started from a question that scientists had maybe a few hundreds years ago, that if you consider 2 points, let's say there is a point A and point B, and let's say you need to go from point A to point B, right? Now how many ways you could have to travel from point A to point B? So there are infinite number of ways that you can move from point A to point B, right? That is, you can follow a path like this, and you may follow a path like that, like this, and at the same time, you can follow the path of straight line like that. You can see that there are infinite number of ways that if you want to go from point A to point B, there are infinite number of ways of doing that, right? So out of these different ways of moving from A to B, if you consider a particle, it will only follow a certain trajectory or certain path out of all these possible trajectories, right? Now, maybe you know that when you need to go from A to B, so why the question is that why is that particular solution is the only valid solution in mathematics, right? So this is the question that actually they tried to answer, and as a solution they had this variational principle at the end. Anybody knows the answer why is that it follows only this one of these particular trajectories out of infinite number of ways? Now if you you know that if you consider as an example in a plane, the shortest distance between 2 points is a straight line, right? So at the end, you would see that as an example, I will show that. But this is actually the problem that they had. Like, why is that that a certain particle follows a very specific trajectory when it when it go from A to B, right? So this is our main focus for today's lecture, and we will derive a mathematical expression to solve this problem, right? So that's the aim of the lecture, and ultimately we will get the Lagrange equation, right? So that's what we will have at the end. Now the question is, let me write it here. The question that we try to answer is why the solution of equation of motion have a particular trajectory. So let me tell out of all possible trajectories. I don't know whether you have ever thought about this, right? I mean, when you consider 2 points from A to B, there is a particular trajectory a particle would follow, and the the question that we are trying to answer is why the particle follow that particular trajectory, right? And now this is bit different in quantum mechanics. For example, if you get quantum mechanics, we used to tell that in quantum mechanics the a quantum mechanical particle follows all possible trajectories, right? All possible ways. If you look at this diagram from A to B, in quantum mechanical language, it would be that it will follow all these possible trajectories, right? So what you would normally do is you just try to find a probability of uh, following a certain trajectory, or probability of having a particle at a certain position in quantum mechanics. But in classical mechanics, we know that a particle would follow a certain trajectory. Now, to answer this question, we will start. So this part is actually very highly mathematical, and we will start a principle called Hamiltonian principle. So that will be our starting point. So that will be. So let me first introduce you this Hamiltonian principle. So what this Hamiltonian principle tells you is, let me first write it here. For any system from time t1 to t2, from time t1 to t2, along a certain path this equation over the line integral I, which we defined in this way. This is the Lagrangian, by the way. So the Lagrangian is a function of q's, q dots, and time times dt has a stationary value. Now in mathematics, this is why you have a certain path, certain well-defined path for a particular particle when it moves from A to B, right? So it basically explains from the Hamiltonian principle. So I will start from here. So what this means is, if you consider this particular line integral that includes a Lagrangian, this will have a stationary value for this particular path that it follows, right? So this should go from time t1 to t2. So let me start from here. So what this actually means is, for actual motion, that means for that particular path, for actual motion, this I should have stationary points. Now when I tell that this I has stationary points, mathematically what that means is, that is the variation of I, or we used to tell as delta I, variation of I should be equal to what? If it has stationary points. Anybody have any idea what this means in terms of calculus? When I tell that the variation of, when it has a stationary points, what should happen to delta I value? That should be equal to what?
So is it 0?
That should be equal to 0, right? So that is the definition, right? So which means this should be equal to 0, right? So let's see how we can go from this point on. So if the variation is equal to 0, then you can write now. There is something that you need to note down here is, in this particular situation, there is something bit different than what we used to have in the in calculus. In general, what you would do is, normally you vary some variable, and then you are trying to find the stationary point, right? But here what we are doing is, we are varying the function itself, and then once you vary the function, then what you are looking at is, then you look at how the integral changes, right? So that's the difference in this particular situation than the previous instances that you had in differentiation, right? When you are trying to find stationary points. So if I draw this in a diagram, it is something like this, that let's say you have 2 points A and B, So it may follow this path, and then after that you change the function itself, right? So once you change the function, then you look at what happened to the integral, right? So that's what you do normally. So I can write it. So let me just have a note here. Function itself, and look how the integral changes. Now for the Lagrangian, you can see that Lagrangian we normally use to write in terms of generalized coordinates, where you have n number of coordinates, right? And just to keep things simple, let me first consider the one-dimensional case and then do the proof for the one-dimensional case, and then we will apply that for generalized coordinates, right? So I am going to directly move into one-dimensional situation here, which will make things a bit easier to understand, right? So let's first consider the one-dimensional situation and consider a function yx. So basically y is a function of x. Now let me write the above integral for the one-dimensional case. So let's assume that this changes from x1 to x2. Now our function f, so I'm going to replace Lagrangian from a function called f. And this is a function of y dash, or you can tell y dot or something like that, and x and dx. Now remember that if you compare this one with the, so let me just, if you compare this one with what you have here with this expression, in instead of time, now you have x, right? For the one-dimensional case, when I write this equation, so instead of time is replaced by x, and then a qi is like y here, and then you should have, by the way, dot here, and qy dot means like dy over dx, right? And for the generalized coordinates, what qy dot means dq over dt. Now for our one-dimensional case, I just use dy over dx, right? So it's just the same case, and I'm just changing variables and then do it for the one-dimensional case first, right? So I'm using I, so that should also have, so I'm looking at such that I should have stationary point. So this is my condition, right? So if I draw this in a diagram, now it's easier to draw it actually and show it to you because it's only for 1D case. So this is my y-axis. Take this as x and this is y. So there is a point right here. Let me take this as x1 comma y1, and let me take this point as x2 comma y2. So basically this so I want to go from x1 to x2, right? So there may be different paths that I could have for this. So that's the idea. So I guess may be easier for you to understand in terms of x and y's. Now there are two trajectories here that I have drawn in the diagram. So let me consider these two trajectories and explain this. Consider the above two trajectories about two neighboring trajectories. Right, so I'm going to consider these two trajectories and show that how I can change from one trajectory to the other one, right? What is the connection between these two? So what I can do is actually I can parameterize the function to show that how I can change from one curve to the other curve. And let me write it in this way. So let's say this is one of the curves, and if I want to go for the next one, I'm going to use a parameter called alpha and another function neta x. Now this alpha is basically the amount of change uh, that I have from one curve to the other curve, right? So that is the parameter that I'm going to use to show the amount of change, right? And this function neta x is the function that shows or define the movement from the old function to the new function. And yx0, this one is the original function. So let me write these things just to be clear. So this one right here, yx0, let's say this is one of these original functions that you can see in the diagram. So this is this is the original function that we start, right? So that is the original function, and then this alpha is the parameter that shows the amount of change. And this one right here, the neat x, is the function. This is the function that defines the movement from old curve to the new curve. right? So I guess now it may be clear for you. So what I'm going to do here is I'm going to have a new function yx alpha. So it can be defined as the older function plus a parameter for the amount of change times the function that defines the move from older curve to the new curve, right? So I can write it in this way. And now, so let me just write here this sentence just to make it clear. Now we can parameterize. So I'm just explaining what I have written here in the equation, right? So we can parameterize the function to show that the change from one curve to the next curve. So it is just the just to explain this equation that I have written here. So let me just name these equations. This should be 5 point, the first one will be 5.1. So let me start from here. This will be 5.1 and this will be 5.2, and this one let me name as 5.3. Right. Now this integral that we are considering I should depend on this alpha, right? Because we are, so that is the parameter that we are going to look at basically when you go from one curve to the other. That is the parameter that changes. And according to this Hamiltonian principle, if you take this integral, now the integral should be a function of this line integral should be a function of this parameter. And then what you need to do is you have to differentiate I, which is a line integral with respect to this parameter. Once you differentiate, that should be equal to 0 if for stationary points according to Hamiltonian principle, right? So that's what we have to do here. Now, so let me do that. So 5.2, equation 5.2 right here now depends on alpha, right? When you go from one curve to the other. So the 5.2, now the integral should depend on alpha. That means if I basically look at the new function, because you can see that in 5.3 now the y depends on alpha as well. So now our new integral will look like from x1 to x2. The function now depends on both x and alpha. So this should be f function depends on, and then y dash x and alpha, because you can see that the new function depends on x and alpha. Alpha is the parameter that defines the amount of change from older function to new function, right? So I hope this is clear for you now. And let me name this as 5.4. Now we all know that if you need to find a stationary point for something like this, di alpha respect to alpha should be equal to 0, right? So this is the condition that we are going to use to do the calculations from here on. For stationary points, this should be equal to 0, right? Um, Let me just write it in this way. Condition for stationary points should be differentiation of this integral with respect to parameter alpha at alpha equals 0 should be equal to 0, right? So this is the condition. Now let's see how we can use this condition, and let me name this as 5.5, right? Right. Now take this in equation 5.4 and let's find di over d alpha, because that should be equal to 0 in order to have stationary points. Now let's do the differentiation. Now you can see that the first term y depends on both x and alpha. That is, when you do the differentiation, first you have to differentiate with respect to y and then y with respect to alpha, right? Because now phi is a function of f is a function of y and y is a function of alpha as well. And then the next one is, this is a function of y dash, and then y dash is a function of alpha, right? So that is for this part right here. And you can see that does x depend on alpha? That does not depend on alpha, right? You can see that even in this expression right here, x is right here, that does not depend on alpha. So which means when you differentiate with respect to alpha, the answer should be 0, right? So this is what all you will have for the expression. Now this will be 5.6. Now from here on, let me just take, so let me just have a note here telling that x does not depend on alpha. Now just let me take this second term only and see what we get. That is from x1 to x2 da by 4 da by y dash and da by y dash over da by alpha. So this is same as you have dx, and here da by y dash means da by y over da by x, right? So you can expand that so that you will have this expression. So all I did was just have y dash written as dy over d, da by y over da by x, right? So then you will have da by squared y over da by x da by alpha. So let me just name this as 5.7. Now if I apply integration by parts for this expression right here, you can see that it is easy to apply the integration by parts for this expression and do the integral. Because of this expression right here, you can directly apply it. So let me write it using integration by parts. Let me do that. So I am going to do the integration of the 5.7. That is, the first term will be da by 4 da by y dash, and then the integration of the second term, that will be da by y over da by alpha, right? Just check this yourself, right? I guess you can understand this. And the integration will be from x1 to x2. So just differentiate this term right here, then you can say that if you differentiate, then you get d over dx da by y over da by alpha, which is the second term here in the 5.7, right? So it should be correct. And minus x1 to x2. Now you have to differentiate the other one, that is da by 4 da by y dash. The remaining term is da by y over da by alpha and then dx. Right? So this is what you get from integration by parts. Now what is the answer for this particular section right here? That for that expression. Anybody can understand the answer for that one? Let me take this expression as A. What would be the answer for that? See that it's going from x1 to x2, and these endpoints for the two curves are not changing, right? So they have the same endpoints. So that should be equal to 0, right? So just think about that. Since the endpoints are not changed, A should be equal to 0, right? Remember that we are just going from x1 to x2, right? Here from this, we are going from this point to this point right here. Those endpoints are same for both curves, right? So this is if I explain a little bit more about this, the idea is when we define this variation between the 2 points, it is just the variation of function between the 2 points, right? So the function varies between these 2 points, but the condition is that these endpoints, we don't vary anything, right? If you look at the function itself, we don't vary anything for that endpoints, right? Because of that, this part should be 0, right? Because of that, now let me rewrite the expression for di over dl for now, which is equation 5.6. Now we have some simplifications with those. Let me write this di over d alpha. So that should be equal to from x1 to x2 dx. We have this term right here that which is not changed, da by f over da by y, and then da by y over da by alpha minus d over dx. Now you just get the second part only in this expression right here, because the first part is 0, and then dy da by y over da by alpha, right? So what I did was I just rewrite 5.6 here, but for the second term of the 5.6 I can apply the solution that I get here for the 5.7, right? Because the first part is 0 and you just get this part right here. So I have write it here in my expression. So that's all I did. Now what I can do is from x1 to x2 dx, you can see that the da by y over da by alpha is common, right, for both expressions. So that means I can take that out from the brackets. So da by 4 over da by y minus d over dx da by 4 over da by y dash, and then you can keep da by y over da by alpha outside the brackets. Let me name this as 5.8. Now you should see now that you have something very look like what you had for the Lagrange equations here, right? And right here you have da by y over da by alpha. Now from the equations that you have, uh, can anyone of you tell me what is the value, or what is the value that you would get for the da by y over da by alpha? What will be that value? This is not that much hard, right? If you look at this equation, the very first one right here, equation 5.3, what is da by y over da by alpha here? That should be equal to neta x, right? Because when you differentiate this equation with respect, equation 5.3 with respect to alpha, the first term yx0, that will be 0, right? Because there are no alpha terms here, and neta x is just a function of x only, which means when you differentiate with respect to alpha, the answer will be just neta x, right here. So from 5.3, da by y over da by alpha is equal to neta x. So I guess you can understand how I have this neta x. Right, let me take this as 5.9. Now let's combine 5.8 and 5.9 to have a final expression for di over d alpha. That is from x1 to x2. I have dx da by 4 da by y d over dx da by 4 da by y dash, and then you have neat x for the for da by y over da by alpha. Now the condition, remember that the condition that we should have is this expression should be equal to what? This should be equal to 0, right? Di over d alpha. Right here we mention about that condition. Di over d alpha. Yes, right here the equation 5.5 says di over d alpha should be equal to 0. So that means you have to take this whole expression and make it equal to 0. Now if you look at carefully the equation 5.5, the neat x is completely arbitrary, right? So because of that, this particular expression right here need to be 0 in order to have this expression equal to 0. So which means you can get this so let me write it here for di over d alpha to become 0. This expression has to be 0. D over dx da by 4 da by y dash equal to 0. Right? This has to be 0. That is because the other term cannot be 0 because the neat x is arbitrary. Right? So I guess you should understand by now that this is same as the Lagrange equation now. D da by 4 da by y minus d over dx times da by 4 da by y dash equal to 0. Now, if I replace the variables x by t and then y by q, what you get is da by f over da by q minus d over dt da by f over da by q dash or q dot, whatever you can call it. This is equal to 0. And you can clearly see that this is the Lagrange equation, right? Now, this is a very, very nice result that you can see that one thing is that you can, one way of telling is this is that the Hamiltonian principle is completely equivalent to the Lagrange equations, right? And in another way, you can see that you got the Lagrange equation at the end as a solution for stationary points, which means when you have these have the equation of motion of a particle or when particle moves from one point to the other point, it basically moves in such a way that this Hamiltonian principle satisfies. And in another way, it also satisfies the Lagrange equation, right? So that's what you can understand here. Other than that, it's the same Lagrange equation. But the Lagrange, once you have this, you can also understand that the Hamiltonian principle, under the Hamiltonian principle, this particle moves from one point to the other point such that it satisfy this condition that you should have a stationary point. So another way, it should satisfy the Lagrange equation. So any particle that moves from one point to the next point will satisfy the Lagrange equation, right? So that's what this principle basically tells you. Now, the good thing is, now for the Lagrange equation, when you prove previously we use this thing called we use the kinetic energy, potential energy, and then wrote the Lagrangian, and then we proved the Lagrange equations, right? Sorry, in previous case, actually we used the generalized coordinates and then constraints to prove the Lagrange equations. And here we did the same thing using Hamiltonian principle, and the Hamiltonian principle is not only for classical mechanics, that is that can be applicable to other areas, which we actually call this as the variational principle. This will be applied for any area. Now, for example, I will do an example for you just to show you how this can be applied to solve some different problems. And one is that, so let me write it in this way. This technique can be used in general to find stationary points. Now, for example, let's see that whether if you need to find the shortest distance between 2 points. So this will be an example. So let's say you need to find the shortest distance between 2 points. Now, so what is the equation of the shortest distance between 2 points? I mean, all of you know the answer for this one. So from A to B, what would be the shortest distance? It should be what? Let's say you take 2 points and you need to go from A to B from the shortest distance. So that should be the direct line. Yes, thank you. Or a straight line, right? Or all of us know that, right? But how can you prove it? If I used to tell that, okay, the shortest distance is not that distance, there is a different way of different curve that represent the shortest distance. If I tell it in that way, how you can prove it, right? Now to prove that, you need this variational principle, right? So that's the beauty of this theory. Now, if you take the 2 points A and B, for example, in Cartesian coordinates, in any distance, any smaller distance ds, because for A and B, there are a number of ways that you can move from A to B, right? You can move in this way and that way, like that, right? Now, for any movement, if you take a small distance in terms of Cartesian coordinates, you can write it in this way: ds square, ds equal dx squared plus dy squared. Now to find the shortest distance, you need to get the integral, right? The idea is, if you take this integral, this is actually what we did throughout this proof. If you take this integral of the function ds, then you have to find the stationary points of this particular function in order to uh, have the shortest distance. Now ds can be written as, I mean, this is a simple problem, but still a good example to show how this theory that we have just derived is applied to an example or a problem. So ds can be written as right, you can write it in this way if you need. Just a rearrangement. ds is equal to dx squared plus dy squared and the square root of that, and I take dx out from that square root so that you can write the expression in this way. Now this is like the function f that we had, right? You have y dash, but you don't have actually y function y. If you now try to write the function df da by f over da by y, since f is in this form, you don't have y dependence there, right? You just have y dash here only. So da by f over da by y is equal to 0, and then da by f over da by y dash is, by the way, dy over dx. So that means that will be 1 over 1 plus y dash squared and the square root of that, and then here also you have a y dash, right, after the differentiation, that is just da by f over da by y dash. Now the equation that we have at the end is equation 5.10. In that da by f over da by y is 0. So what we have is d over dx times da by f over da by y dash. So d over dx times da by f over da by y dash should be equal to 0. And here d over dx we have, now the da by f over da by y dash means this is equal to 0, right? That means y dash over 1 plus y dash squared should be equal to a constant, which is equal to, let me see this is c, this is a constant, right? Now you can just so that c will be a constant. I think you can do the rest of the things. I will just write down the note just to complete it. This is valid only if, let me take another constant y dash equal a, and a is actually related to c by this equation a equals c divided by 1 minus c squared. This part, I guess I'm not going to explain it. I guess you can just do it yourself. It's not just replacing the constants here. And this will give you a straight line or equation of the straight line y equal ax plus b or something equal to that. And this is the equation of straight line, right? You can see that you already know that this should be, the answer should be a direct line or a straight line, but you can prove it in this way, right? And you can see that this is actually not classical mechanics. This is just a simple geometry. This way you can also prove that if you think about a sphere, on a sphere the shortest distance is we called as a geodesic. So this equation of the the equation of the geodesic also can be proved using the same principle if you need, right? But I will just do only this example, and maybe in your tutorials there may be some other examples appear, right? Now this is the proof that we just did is for one dimension, but if you want to do it for n dimensions you can generalize it. So let me just write it here, so that n dimensional proof will give you the general Lagrange equation. So this will be generalization to n dimensions. So that will be, if I write the variation, that will be delta L Qy dot t. This is how I should write it. Then you will get what you would get at the end is, after the calculation, d over dt dabba L over dabba Qy dot minus dabba L over dabba Qy equal to 0. Now basically you have set of n equations here. And this is also the Lagrange equations. Right, so I hope this is clear for you now. And so this is actually another way of proving the Lagrange equation. And what we did was, if I summarize, we started from the Hamiltonian principle right here, and then in order to go from one point to another, point A to point B, we started from the Hamiltonian principle and stated the Hamiltonian principle states that this particular integral, line integral I, when it goes from one point to another point, uh, it should have stationary points. So in another way, for one dimension, if I convert everything to one dimension, what that means is, if you make a small change in the line integral, when the when function goes from one point to the another, if you change the path by some amount, that path can be written in that new path can be written according to this equation 5.3 using this parameter alpha and the new function neta x, and then the line integral is a function, line integral becomes a function of alpha, and then you differentiate the line integral with respect to alpha. After you differentiate it and then apply the integration by parts for the second term, and then you can have this final equation, which is 5.8, and then you replace dy over d alpha in the equation 5.8 with neta x according to the equation 5.3, where you would get an equation which is very similar to Lagrange equation, and in fact it is the Lagrange equation. And then we solved a simple example just to explain this method, which is actually not related to classical mechanics. That is just to find the shortest distance between 2 points, and then you can generalize this into n dimensions using the Lagrangian to have the same Lagrange equation, right? So that's what we did. Basically, this is another way of proving the Lagrange equation, and at the same time, you can see that the Lagrange, in another way, Lagrange equation means or the equation satisfies this stationary points condition or the Hamiltonian principle as well. So those are two equivalent things, right? Right. So let me. Anybody have any questions up to here? It maybe you, since this is a mathematical proof, if you have any like issues between steps, just go through it, and this same proof is available in the lecture in the ICTP that I have posted, which have actually more information sometimes than what I am telling here, because I have another section that I have to cover. So just go and look at it, and also the book also has explained the same thing in more detail, but maybe it has used different symbols and different steps, but it's basically the same content in the book. This is actually section 2.2 in the book. Basically chapter 2 is about calculus of variation. We are now in the chapter 2 in the book, so you can look at that as well. And anybody have any questions up to here? Now, if you look at the Lagrangian equation and generalized coordinates, the conservation laws means actually functions of q's and q dots, where they will remain constant during the motion. Just give me a minute to fix this thing. Right. So the Lagrange equation basically means, the conservation laws actually means in terms of the Lagrange equation. If you remember, when you write this Lagrange equation, if you have functions of q's or q dots, that means basically if it is Cartesian coordinates, that would be positions and velocities. So if they don't change with the time during the motion, those will be constant, right? So those are actually what we called as conservation laws at the end. Now this the topic of my lecture is actually conservation laws and symmetries, and this is actually one of the very interesting features or very interesting topic in classical mechanics, how these conservation laws are attached to symmetries in space or in nature. Now, actually, we are actually basically done with the very basic theories that we should learn in classical mechanics. So that's actually Lagrange equations, and everything that we are building or learning from now on will be based on the Lagrange equations and different. We will have like different theories that we have to learn, but all of them are actually based on basically on the Lagrange equations and also on the Hamiltonian principle. Now, the conservation laws and symmetries are also the same. One point is that in our context, when we are talking about these Lagrange equations, the conservation laws means actually basically functions of generalized coordinates or generalized velocities that remain constant during the motion. So let me write it first. In our context, conservation laws are functions of Qy's and Qy dots that remain constant during the motion. Now these constants are actually called as first integrals because you know that we have q's and q dots which we called as generalized coordinates and sometimes generalized velocities in our equations, and we don't have like accelerations, right? So those are actually second integrals. So because of that, these constants are also called first integrals. And the third one is the one that we actually talked about, the symmetries. Now, all these conservation laws actually that we are learning, they are actually related to some kind of symmetry of a system. So this is the interesting point here. Any conservation law is always associated with the symmetry of a system. Now, as an example, uh, we will talk as the next step. Okay, so let me just write it and just talk one by one so that you will understand what is the conservation law and what is the associated symmetry in the system for that particular conservation law, right? Now, the one thing that you have to make sure that you understand here is that it is true that you probably have learned about conservation laws before. For example, conservation of energy and conservation of momentum may be two things that are very familiar for you, that you have even learned using in your A levels using Newton's laws. But here we are actually talking the same thing using a different. We are looking at the same thing in different way. That is how we actually connect these conservation laws with the symmetries that we have in nature, right? Or in, this is very important in physics. Even from now on, when you learn these conservation laws, think about the law conservation laws in that way, right? So these constants or conservation laws are also, let me write this, these conservation laws are also related to also related to the symmetries of the system. Basically, the conservation laws come from the symmetries of the system. Now let me start doing few examples how these to show you how these conservation laws and symmetries of systems connected to each other. Example number one. Now, rather than actually doing these three myself, I'm going to assign you three questions and you have to answer this and post it to the LMS, by the way. Because I was looking at take some answers from you. Seems that either you don't like to answer or maybe you can't, maybe you don't have a good connection to give me answers, or maybe you are not here, I don't know. So what I am going to do is I will start some of these problems and leave for you as three exercises, so that once you are done I will discuss this on next day, right? So for the number one is think about this scenario. If let's say if you have a system, if a system doesn't change explicitly with time, then what happened? So that what that means is the system is same at different stages of time, right? When the time goes on, the system doesn't change, right? System, that is, you have a system that is same at different instances of time. Now, if the system doesn't change with change explicitly with time, I want you to show something, and so I'm not going to do this. So I'm going to assign it to you as an assignment. That will be, so you, let's say you have this Lagrangian, which is function of qy's and qy dots and t's as a function of time. So if the system doesn't change explicitly on time, I am going to write one thing. That means, what is the answer for dabba L over dabba T? If the system doesn't change with the time. If anybody would like to answer, you can answer or you can just post it. Sajini, yes?
Zero, sir.
Zero, right? Yes. Thank you. So I am always getting answers from only one or two or three students, right? So how about the others? So either they are not here or they may not hear me or they can't understand anything or something. So one of these, or maybe all of these, right? Okay, so finally I got three answers. Still, I don't know. Some of you seems to be very silent. Okay, so most of you have answered this time. Thank you. So make sure that you just listen to the lecture and answer it, right? I mean, these some of these things, for example, like this variational principle and stuff, these are theories that I have to go through the proof, and there is no other way around doing this. Rather than I ask you to watch something and feel it, but I would do that when we start the lectures next time. Right, thank you. Since you gave the answer, let me go through this. Dabba L over dabba T equal to 0. And I want you to prove that this will be 0, your answer that is correct. And after that, go through the proof, and at the end, show me that you will get. So I don't want the same answer, right? Because I'm just going to write something here. Q I dot dabba L over dabba Q I dot minus L equal to 0. Right. So starting from there, what you have from for the dabba L over dabba T, and considering the Lagrangian L Qi dot T. So try to complete this and find this answer d over dt times this one is equal to 0. What this will mean is you will get Qi. Okay, so let me write it in this way. So starting from here, show that this expression, that is the question is show that Qi dot times dabba L over dabba Qi dot minus L equal to a constant which we called as E. So this is a constant, right? That is a constant. And then after this using this constant, you will realize at the end that this constant is actually energy. Then the second one is show that if Lagrangian is equal to this function, that is Lagrangian is equal to, you know, that the kinetic energy minus potential energy, and the kinetic energy is a function, only a function of Q and Q dot, and then potential energy is, let's say, U is only a function of Q. You need to show that that E that I am talking here, E is equal to potential energy plus kinetic energy, right? So this is an exercise for you to finish, right? So I'm not going to go through that. So the idea is when you start from the Lagrangian, if the Lagrangian does not depend on time or explicitly depend on time, we also call this as the system is invariant of time. Then what happens is the energy is conserved. So let me write that here. So I'm going to leave this proof for you. We will come back and discuss it next day, but make sure that you try it yourself before I do that, right? And this is also available in the lecture that I have posted. So just go through and look at that lecture. At some point, this same proof is available there as well, right? Remember that I told you that these lectures that I am posting from the ICTP, so they are uh, nicely aligned with what I am doing with you, right? Basically, my notes are most of the time based on that lecture series as well. So you can go and find the answer in that YouTube lectures and fill these gaps in the note. And so finally, the conclusion from here is that if the Lagrangian doesn't depend on doesn't depend explicitly on time, so we also used to tell that system is invariant for time changes. Then the energy is conserved. Right? So this is another way of uh, conserving the energy, and energy will not change with the time, right? Energy is a constant. So basically, you have learned about the conservation of energy before as well, but the interesting thing here is you can just looking at the Lagrangian, you can tell that the whether energy is conserved or not in a system. So what you just need to look at is whether the Lagrangian is depend on time or not. So if the Lagrangian does not depend on time, then the energy is conserved, right? Does not basically explicitly depend on time, which means it should it you will see that t as a function in the Lagrangian. Then I mean, if t is not there in the Lagrangian function, which means that it is uh, the energy is conserved in that particular system. Now let me ask a question regarding this. Now, anywhere that you are in right now, you probably have a clock with you, right? Now is the this is actually a very simple question, but let's see whether you can answer for this one. Is the clock that you have in your wall or in your hand, is the energy is conserved in this clock? Think about clock as a system. So if the clock is a system, is the energy is conserved or not? There are only two answers. Either it should be yes or no, right? Just a simple question that I am asking. Is the energy is conserved in your clock? Now you can answer this. Just think about Lagrangian and whether it how it works, and then based on what you have just learned, you can answer the question whether the Lagrangian is whether the energy is conserved or not in your clock. Okay, I have one answer. How about others? So let's take a vote now. Everybody, I will wait everyone to give an answer and then see which one is the correct answer. Okay, I have four answers. In fact, five answers. All of them are yes, surprisingly, because maybe. Okay, now I can see that majority says yes. Is there anybody who tells no? Okay, so it seems to me that everyone is agreed with the answer that question is yes. I just can't understand why you tell yes for that, because if you think about clock as a system, by definition, the clock is something that change with the time, right? Anything that changes with the time is a good clock, right? So if the system is changing with the time, what happens? So it cannot conserve the energy, right? So energy is not conserved in the clock, right? I just can't understand under which fact that you used to told that. Oh, okay, so I got one answer because the pendulum is moving. Well, oh, you think about that it transformed the energy into another form, right? Yes, I think I should have asked. Yes, that's true. I should have asked the question in a different way. Is the mechanical energy is conserved in the system, which I guess I missed that, right? So let's say if it is the mechanical energy, then I guess you may agree with that, right? It shouldn't be conserved. So let's keep it in that way. Let's say the mechanical energy. So I think I should have asked whether the mechanical energy is conserved in the system. Then the answer should be no, because the clock by definition is changing its time with the time over the clock. If you think the clock as a system, that it is something that change with the time, right? Clock is changing with the time, which means the Lagrangian should have a time appearing there. The energy is not conserved. That's what I was thinking, but I guess some of you have think it in a different way, that the energy is converted into some other forms. So I think my answer question is not correct. It should be mechanical energy. Then yes, right. So this is about conservation of energy. Then there are two other conservation laws. I am going to give you two another conservation law that it is actually the conservation of so let me get the second one, that is homogeneity of the space. So what is homogeneity of a space? So that means when you translate a system by some amount, it will not change, right? So that is, let's say when you have when a system moves or translates, let's say you have in at a particular point at a position RA, then you move a amount of epsilon up to here. So that is called a translation, right? Moves in space. Consider a translation called RA equal RA plus. So it's initially it's at a position, let's say at RA, and then it moves a distance of epsilon like this. So this is a small displacement, and then you can starting from here and using the Lagrange equations just show that at the end the momentum is conserved. So let's say PA is the momentum. So there are a few steps in between that. So what I want you to do is just go to the lecture that I have posted, which is a YouTube link. Go through the lecture, and at certain points in the lecture, these proofs are exactly there. So I want you to look at that lecture and complete these steps that are in between here, right? So make sure that you do it, because I may or may not do it in the next time, and these steps are very important. The reason that I want you to go and look at it, and I want you to build that skill that you go and look at the video and understand it, and then write it down yourself, right? So these are just uh, not that hard to get from that video. If anybody have difficulties like getting these videos due to internet or something like that, then let me know. But I would like that you go there and go to the LMS. I have post the relevant link there, exact link, so that you don't have to look at any other video. If you go to that particular video, this should be lecture 5 as far as I remember. So just go to that particular video. It has the proof that I previously did. You can watch that as well. And then once you go through the lecture, it will be 1.5 hours. Uh, then at some point you will see this section about symmetries and conservation laws, and he started proving this. Uh, there are actually two things that you will learn there. One thing is the physics, and then also how to understand these lectures, and this will be a good training for you as well in terms of English, because you will actually learn a different accent, because this professor that who is doing this lecture is a French professor, so his English pronunciation is a bit different, so you will be able to learn that as well, and you will get used to it. And these are important after 2 years for you when you are applying for a postgraduate. It's not just the subject that you are learning, your English should be improved as well. So I would like that you go there and check this, and just two small sections that you have to fill for the first time, right? And depending on how you go, then I will little by little give you few more exercises like that to complete in the note, right? Rather than just writing everything by me, right? So I guess so I would like to stop from there for today's lecture. Anybody have any questions? And as the last step, I will go through something called cyclic coordinates in the next time. So that is also actually related to these conservation laws. And then a little bit about conservation of angular momentum as well. Now, if you go and look at this particular video that I ask you to watch, it has all these things as well. So if you need to complete the tutorials, uh, this information is there. Actually, you don't even need to wait for the next lecture, but within the first 15 or 20 minutes I will finish that part in the next lecture, and then move into the next section, which we learn something called Lagrangian multipliers. That will be our next lecture. Anybody have any questions up to here?